Thank you. Thanks everyone for coming to this early hour. It's a pleasure to talk about this project. I did brag with the title. Sometimes bragging is necessary to get into the front row. Here I am. It worked. They accepted the talk. That's great. So I think from the little bit of research that I've done, it's not only Australia's largest blue-green infrastructure for urban cooling, but potentially worldwide. I haven't found any other published information about a similar project like what we've done at Sydney Olympic Park. Now, here's a vision. It's the 2050 master plan vision for Sydney Olympic Park. And what this image shows compared to what Sydney Olympic Park looks today is there's a lot of densification going on with high-rise apartment buildings. Today, the urban population in Sydney Olympic Park is 8,000 people, and it's expected that by 2050, we have an urban population permanently living at Sydney Olympic Park of nearly 40,000 people. Until 2036, it's about 28,000 people, so rapid development now, but further densification. So the two urban cores that you can see with those high-rise buildings will have a higher density in capita per square meter than Manhattan. It will be really dense. And of course, these people have only balconies. They have no gardens. So the green space that they need to decompress, to meet with friends and family, to throw a frisbee and a footy, have a barbecue, that's the outside green space, and particularly Bicentennial Park, which you can see, I think that's the laser, yeah, which you can see on this southeastern corner. That's Sydney Olympic Park's Bicentennial Park, a parkland completely built on landfill. So there's lots of nasty stuff underneath. It is sitting on very shallow soil, 30 centimeters to 100 centimeters only, until you get to a capped lens of clay. And that, of course, means it's highly prone to drying out in summer. It is irrigated throughout. And here's an image of the park, how it looks today. What we did with SIMPACT was take over the irrigation system, use AI, machine learning, and geospatial modeling to provide the optimal hydration for every plant within the park to give us maximum transpiration rates in summer when it's hot. So the whole park is now managed, and I'll show you a few images of the applications that we developed for taking over the park irrigation system, where we can switch. It's like a switch that we can flip from keeping plants alive when, for example, we have water restrictions, which we do have in Sydney, believe it or not, every now and then, to maximum cooling during extreme heat events. It's a very diverse parkland. We have about 200 sites that we can irrigate individually, switch on and off. Irrigation is only during the night and not during the weekend. So we only have limited windows, and we need to be very smart which parts of the irrigation system we switch on and off to, throughout, let's say, a course of a week, water the entire park. We use about 300 sensors throughout the park, 200 soil moisture sensors, 50 LoRaWAN above ground sensors for temperature and relative humidity. And we also have 13 weather stations, 7 within the park and 7 in the nearby urban areas, to be able to compare what you've just provided us with from China. Dr. Peng or Professor Peng, we do something very, very similar. We do combine in our AI that we're using forecasting from Bureau of Meteorology forecasts for the particular area with nowcasting, the current conditions in the park, and hindcasting, where we can use all the stored data that we have coming out of the park, where we know under which environmental conditions we had X% soil moisture and Y% irrigation, what kind of conditions that created. So we can use all the data that we're storing over time to learn and make our irrigation application better every day. There are several thousand iterations that are running every day to improve the application of irrigation water. We use machine learning in a way that is self-learning. We also have a web page where you can, as a park visitor, check out live data feeds. Where's the coolest spot where I should have my picnic? Where should I not walk with my dog because it's really hot just now? There's a lot of information that is live streamed to this web page. we also have a separate web page for the management of the irrigation system. This is the rough architecture of the overall project. You can see the different feeds. We've got data coming in from our sensors in the park on the left. From the top, we get the Bureau of Meteorology forecasts. We feed that into the green box, which is basically SIMPACT. Within that green box, you see at the bottom the red box, which is where all our machine learning happens. This is also where we do the digital twinning of the park, where we have all this information about the park, process that, and then get to irrigation commands that we send out to the right. You can see there's a control element where we have irrigation commands being sent into. It's called Field Mouse, which is the software that operates the 200 stations in the park to irrigate. These irrigation commands are then executed, and this is where the loop closes. We get the information of how much water was distributed and how that changed soil moisture. And we know for each of the 200 sites where optimal soil moisture conditions sit, because it's lawn or it's native forest block or it's garden beds. They all have different requirements. They may face to the south, may face to the north, are on a slope, and so on and so forth. All this metadata is stored for each site, and the machine learning responds to these particular applications. What then happens is we get this feedback loop of how irrigation was provided, and we pick that up with our sensors to then optimize irrigation for the next run. And for example, stop irrigation if we know from the Bureau of Meteorology forecast that in 2 days we have a rain event predicted. So we can also use these forecasts to schedule our irrigation events. Now here are a few analytical graphs that you get as a manager of the system. This is a little picture that shows you in the center where your station is. In this case, it's C84 station 13. Thank you. You see soil moisture conditions on the left. We separated it in very simple terms in terms of saturation, field capacity, and wilting point for the particular plant species that grow on this site. On the very right-hand side, you get some information about the sensor quality. So these LoRaWAN sensors, how much data are they sending? Are they sending regularly? It's a lot of technical information also about the soils themselves. We do, and I don't show all of the graphs that you get from SIMPACT every day. These are sent to people that need to know every day at 10 o'clock. There is soil moisture information in the bottom graph. There are rainfall events, irrigation events in those blue bars where we actually switch the water on and off. And importantly, we have these two lines, the green line and the red line. These are the predicted, from machine learning, predicted soil moisture conditions for this particular spot for the next 7 days. You can see there's a purple line down here. This is this is the forecasted rainfall. So we do see a little bit of rainfall coming. Therefore, we're not irrigating. Otherwise, you would see this green line here spiking like the blue line. That would be the indication that we want to irrigate. And these are two lines where we have the soil moisture development without irrigation and the soil moisture if we want to have cooling application. So if we still add water because we still want to bring more water into the system. So we can see we're never dropping below this green line, which is our optimal soil moisture condition for this particular site. And that means because both lines are not dropping below the green line, we don't need to irrigate. This is just for managers to double check that the system is not actually providing false information. There's also information on the very right-hand side about each individual sensor. We have two reports. One is the compact report where only problems are provided. The other one is a full report for our 250 sensors, the LoRaWAN sensors particularly, about the status of the battery voltage, because once the battery is below 2.3 volts, the sensor basically cuts out. There's information about when the next irrigation event is scheduled for this particular site, and so on and so forth. All linked to web links that automate emails that are sent to us to then look if there's a problem and check if the system is operating in the way that we want it to operate. very interestingly, just in the previous talk, we've seen that there are park warming effects, not just park cooling effects. We find the same. We also calculated delta T, like Professor Peng calculated it against those weather stations that we have in the park and those that we have in the urban core. You just see two examples here, how our weather stations look in the park and in the urban core. We see very extensive nighttime cooling. We do see on average in our last year's summer, which was a La Nina summer, wet and cool, an average park cooling effect throughout summer of about 0.4 degrees. So the park was 0.4 degrees cooler, even in wet and rainy weather. That's a great result. But we're really looking forward to what happens in the La Nina and in El Nino summer that we're anticipating to happen actually this year. So we will continue to run this system. It currently operates. We found funding for another year to have it running. It's fully operational now. There were irrigation reports that I just got yesterday where we irrigated about 117,000 liters throughout the park because it's really dry. We're going through a very dry winter at the moment. So irrigation, unusual irrigation is also required during winter. To sum up, the IoT, so the LoRaWAN part of our project is providing very effectively some amenity for the community and even the growing community of the park, because pressure for the park and therefore nice park presentation will become increasingly important as the number of people increases that live next to the park and use this as their backyard. We are able to maximize the park cool island effect and therefore have a very effective tool by managing water in the park the way that we do to maximize cooling in summer. So a very effective climate change adaptation tool, really. And we're looking forward to use this technology, as I said, in the El Nino summer that we're anticipating, because that's where I think we will really see the benefits that we can generate by using our AI-operated irrigation system for urban cooling. Thank you very much.
Perfectly the time. Sebastian, any questions?
I'm just curious about how much it would cost to operate the model. It sounds like you've done all the hard work, and there's probably not a lot of cost to keep it going.
So you were asking about the cost, the operational cost to run the system. I can openly talk about all these numbers, no problem. We received about $3 million of funding to set up the project. We had another about $3.5 million of in-kind contributions. So the overall project value to develop this whole operational system and all the sensors and all the IoT technology behind it is about $6 million. We need to run it on fumes for a year. We need about $80,000. That's just the platforms in the background and the maintenance of all the capacity of calculation. There's the saying that if you do that on your laptop, it probably would need 2 days to run the calculations, which we do with the capacity that we have within Eratos and Synapse, the platform that we're using, within 20 minutes. So it's really important for us because we do this every day to use high capacity computing. $80,000 is about the 4 companies that provide us with the various services. We stream data from the park to Perth, to Tasmania, to Newcastle, and back into the web to have park visitors look at SIMPAC temperatures. So there's a lot happening to maintain this kind of system.
Which is not much when you consider like 4 horticulturalists walking around.
Yeah.
Correct. Yes, and we're also anticipating, of course, that you save maintenance costs in the park because the system detects, for example, leaks, which otherwise you would only detect if you are in the park. And that hour that you're in the park, someone needs to pay that. So all of these things are, of course, savings that you can reap in as well.
Right, well, it's very cost effective and very effective.
Very effective. Thank you.